In this recording, we will be doing an example about using logistic regression. It's about estimating logistic regression model. As we discussed, we used logistic regression as one of the tools that we use to estimate the response variable when the response variable is qualitative or categorical. So we are expecting now to have a scenario where the response variable is categorical. Again, I am working on chapter 9 project. So I created a project, chapter 9, it contains all of the files. And again, we are staying in this directory. That's why it's easy to load our dataset. So the dataset called default. And what is the question? Automobiles, including cars and light trucks, are the most held non-financial assets among Americans, which are most financed through loans. Peter works in the car loan division of a major commercial bank. He wants to use a data-driven strategy to identify borrowers who are likely to default on the automobile loan. The file contains historical data for 400 customers, including information on whether the customer defaulted and the corresponding loan-to-value ratio, LTV, in percentages, FICO credit score, the age. So we have three variables. Consider logistic regression model for default using predictor variables LTV, FICO, and age. So we are going to estimate regression model for this one. So this is the data. Let's explore the data, look at the variables that we have. So we have a default. Values are 0, 0 is 1, 0 is not defaulting, 1 is defaulting. The customer or borrower is defaulting on loan. LTV in percentages, credit score, then the age. So we have to estimate the default function. So this is the point. And let's explore the data. So look at the data that we have, structure of the data. We have numeric values. That's the default, but basically it's a factor, it could be 0, 1. But here it's classified as numeric. That's what we will see. What is the impact of this? But we have to make sure that none of these are character. If it's character, you have to change it to either dummy variables or factor. It depends on that situation. So we have the minimum, maximum, maximum. So we have other functions to investigate the data, but these are enough for now. Let's now estimate the logistic regression. So estimate the logistic regression model to find the predicted probability of default given the average values of LTV, FICO, and age. So we have two parts here. We have two things to do. Number one, you have to estimate the logistic regression model. So let's call it logistic model. When you estimate the logistic model, we are going to use a function called GLM, Generalized Linear Model, GLM. And this function is specified for other, actually we can use this one for regression as well, but we can use this function for many other models, linear models. One of them is the logistic regression. So again, this function contains arguments. We'll be using 3 arguments. If you look at the arguments, you can see so many arguments. We're going to only discuss 3 arguments: the formula, and the family, and the data. The formula, family, data. If you want to keep it that order, that's sometimes I recognize if you switch, for example, the second and the third order, the second and the third argument. But we will stick to the format or to the order. So the default as a function, this is the function, it's called default. So default, we're going to write this in terms of other functions. So tilde dot, that means we're adding all of the other functions, comma. The second argument is going to be the family. The family is binomial because we have binary response variable, which is 0, 1, binomial, comma. The data is going to be my data. I call it my data. If you'd like to specify, then if you'd like to write data is my data, that's also. If you leave it my data as you used to do, also this is fine. Both of them are correct. And you can try, you can try and see. After that, I would like to look at the summary of the logistic model. Let's run these two. So this is the formula of the default. What if you change this? For example, someone's going to say, why if I write FICO and age? Are we going to get the same thing? Run this and try. We have a problem with this because we have here. So we get the same thing, right? So this is the model. This is the intercept. This is the LTV. This is the FICO. This is the age. All of them are significant. But as we said, we cannot interpret these estimates right now in the way that we used to. This is logistic regression. It's not the one unit change of the FIC leads to increase, by 0.02 in the response. No, this is not the way that we're going to do this. But first, because the question says estimates, so we're going to write the estimated model. So the estimated model And you can go to the lecture and look at how the probability look like, how the model look like. Is going to use latex or mathematical terms so you can see the writing here. You have to be careful. So going to be hat is the predicted probability. What we're doing, default. Let's say default. Probability of default. So this is, we have to be under the text. I don't want to write this. I'm going to keep it P because I have to use another function called text. And equals, I'm going to have a fraction because these are fraction. This is the way that we write fraction. We have, what do you call it? Backslash frac. Then we have curly parentheses twice. The first one for the numerator, the second one for the denominator. Exponential to the power. Let's go look at this. The intercept was the intercept. This is the intercept. I'm going to copy this. I'm going to take just the first few digits just to make our life straightforward. Yeah, because we have a power, so I'm going to add, we have to be very careful here. I'm going to add another curly parentheses, close it immediately because I'm going to put so many terms inside and they're going to be the power of the exponential plus this is the second one, right? For LTV, this is LTV. I should have another one. Here we go. Plus, this is the FIC, the credit score one. I'm going to take the few digits only. The very last one is the age. We take the few ones again. This is going to be the numerator. For the denominator, again, we can do the same thing, plus 1. So I'm going to copy the E thing, the exponential. Be careful with the curly parentheses. Here we go. So this is my predicted probability. This is my predicted probability of a person who's gonna have, or a person who's defaulting. Is going to, we're gonna have all of these. So for instance, if I give you a person's LTV score, FIC score, his age, then you can tell me the probability that he is going to default on loan. And this is the second part of the question. The second part says, let me go. Find the predicted probability of defaulting given the average values of LTV, FICO, and age. Just in general, if I give you the LTV, the average of these values, what is the chance that a person is going to be defaulting? So before we do this, we have to find the average of these values, right? So let's get the average of these values. We have two options. To find the average, LTV, FICO, and age, you either use the function means that we used before, or you can use, because we have many variables we'd like to do, we either use mean for each variable, right? For each variable. Or let me introduce a new function, or we can use column means. So go to my data, look at the columns, give me the column means, the mean for each column. So I'm gonna make it easy. Column means easy for my data. So I'm gonna give you the mean for everything, for all of the columns, including the default. I don't care about the first one, but we care about the others. After getting the mean, we can now predict the defaulting stuff. So now let's find the predicted probability of defaulting. Predict. Again, we're gonna use the model. Do you remember that? We're going to plug in values into our model. So this is the logistic model, and we're gonna plug in data frame values. Data frame. LTV has to be what? 77.78, comma. Credit score has to be what? 6684, comma. 8.4, sorry, comma. Age has to be what? 42.1. I got a problem. What is the problem? Logistic. Yes, I remember what is my problem here. This is important. We have to have another argument that we have to tell R that we are predicting the response variable. So I'm going to add another argument called type. I'm going to call it response. So I'm not going to call it, it is the way that we said it. It's called response. Here we go. So what we got? We got the predicted probability of a borrower with the given scores, with LTV 77.7%, credit score 668%, age is 42 years old, defaulting, the predicted or the estimated probability that this borrower with these values defaulting is about 2%. Very low. I mean, very low for me. I don't know for the company, for the financial institution. So it's 2%. So this guy's gonna default. It's 2%, about 2%. So Remember again, when we predicted, we have logistic model, we have the data frame, the numbers that we would like to plug in into this function, then we added the type response. The type response because we said that we tell R that, hey, we have a regression model, we have logistic regression model, and the response variable is 0, 1, so that's why we are predicting the probability of the event occurring. But in the linear regression, we have never added the type because the model predicts continuous outcomes, not probabilities. In this case, we are predicting probabilities. Then we're telling R that, hey, because we're predicting a probability, we have to specify the type. The type is response. For the linear regression, we don't do this. You can use this. You can now write the cat, let's say, concatenate this. You can write the predicted probability of a borrower with given scores defaulting. I don't know if the wording is how much is all of this, right? So let's call it P for the sake of, convenient. Is 20 is this, right? If you'd like to do some calculation, then you can do this. You can, by the way, you can say I'm going to multiply by 100%, by 100. And I'm going to add one more, concatenate the percentages. Hey, here we go. So 2%. If you are not happy with all these digits, you can add the round function. Round it, give me 2 digits, let's say. Here we go. Does that make sense? I hope that it's easy to be understood. Anyway, it's not necessarily everything I've done, but it's good to learn these basic skills. We're going to do this again, and the question says now, find the probability and odds. So we're going to find 2 things now of defaulting given these values. So we're going to have this again, because we're going to do this the same. We're going to do the same thing. I'm going to copy all of this, because we're going to repeat this, but we're going to change the values. So LTV 70, there are people outside, removing the, no. So I don't know if you can hear this or no, I hope that you don't. Anyway, so 70, 650, and here we go. So we got about 3.4%, 3.4%. And I'm back. I stopped for a while until they finished. Anyway, so we are finding the probability and odds of default given these. So we have found the defaulting probability, the expected probability of defaulting for a person with these scores, right? We got about 3.4%. And we have to get the odds of defaulting. So we have to calculate the odds. How to calculate the odds? If you remember, the formula says that we divide P by 1 minus P. So let me write this. We use, to find the odds of defaulting, we use odds equals P. Let me use a fraction, frac P over 1 minus P. To be honest, it's not P, it's the predicted probability, which is P hat. It's P hat. You have to add hat for this defaulting. So what is the odds of defaulting is we are going to divide. So I'm giving, this is a probability, I'm gonna call it, should be, anyway, it's probability. Let me call it P hat. It's P hat divided by 1 minus P hat. Then let's look at the odds. So the odds of defaulting is approximately 0.034 compared to the odds of not defaulting. It's negligible. It's about 0, right? So we said if the odds are much less than 1, which is in our case, that suggests that this event is less likely to happen. It's kind of people, they're not going to default with using these scores that we have right now. A person with these scores is likely not going to default into loan. So yeah, we may give him money, right? So let's give him some money. Find the corresponding probability and odds if the credit score is 700. So we're going to repeat this again, but maybe we have different scores. I'm going to copy the whole thing here. Let me copy the whole thing. So I'm going to call this, it's not P, it's another P hat. So I'm going to change it, but the score is going to be 700. So let's call this P hat 0, P hat 0, P hat 0. So what is the probability of a person who's going to, let's see the probability first. So the probability is, getting a higher score. Look at the defaulting. The probability of a defaulting person is about 0 because he has higher score. Look at the impact of the credit score. Also, let's look at the odds. So the odds also. So this person, you can give him money without even thinking about that, right? So this is number 3. Number 4, it says interpret the percentage change in the default odds when each predictor variable increase by 1 unit, holding the other variables constant. Now we are talking about the B's we found. Interpret the percentage change in the default odds when each predictor variable increases by 1 unit, holding the other variables constant. Now we go back to the table, or to the formula, right, that we created, which is this one. We look at the betas, or the B's, these are the B's, or we look at these numbers, So let me copy this, look at the summary. So to answer this question, we are going to look at the summary. So for the LTV score, for a 1 unit increase in LTV, the default odds increase by 17%, about 17%. For a 1 unit increase in the LTV, the default odds is likely to increase by 17.29%. For a 1 unit increase in the credit score, the default odds is likely to decrease by 2.3%. And for a 1 unit increase in the age, 1 year in our case, the default odds tends to increase by 3.48%. So we can write all of this down. So for a 1 unit increase in LTV score, the default odds, the defaults on loan increase by, it was I think 17.29%. For a 1 unit increase in vehicle score, the default odds decrease by 2.3%. Finally, for a 1 unit increase in age, the default odds would increase by 3.4%. So this is the explanation of it, or the interpretation of the percent change in the default odds when each predictor variable increased by 1 unit, holding other variables. This is the partial effect of the variable on the odds of the default. Extend the model to also include age squared to find the corresponding predicted probability of default. So we can do this. So we can basically add a squared effect. We can add squared, we can add other effects. Maybe we are going to get a better model. How do we know a better model? As we said, we use one of the techniques is to calculate the performance measures, which are the accuracy rate, the sensitivity, specificity, and we may again conduct cross-validation method to improve the productivity power. To compare these, we're going to use cross-validation techniques, right? So let's do number 6 now, or 5, to extend the model. Let's extend the model. So we are going to call this WAD logistic. It's GLM. We have default, our response variable. Then we have tilde. Then we have LTV plus FICO plus age plus, if you add term squared, if you remember, we add I. Then it's going to be family. It's binomial. Then we have my data. Make sense? After that, we're going to find the summary of this quad logistic. So we got all of these. All of them are significant, by the way, as the previous one. But we don't know which model is better because we did not find the accuracy rate for both of them yet. So what did we find? We find the model, then find the corresponding predicted probability of default. We did. So how do we write the estimated model as we did before? Just we add one more term, which is negative 0.010872 age squared. Then is the age squared statistically significant at the level 5%? The answer is yes. It is significant of all of the predictors. Both models show slightly significant predictors. Both of them. This is significant here, significant, right? For all of the variables. By the way, for the goodness of fit measure, we can look at a measurement I did not explain in my lecture, which is residual deviance. We're looking for something low, residual. It's kind of the error. This is 121. The previous one was what? 160. Also, we have an AIC, by the way. But anyway, let's focus on this right now. This is 160. This is 121. So in terms of goodness of fit, which one has a better goodness of fit? The second one suggesting a better fit to the data compared to the first one, because we have lower residual deviance. And the residual deviance is a measure of how well the fitted model explains the observed data. And yeah, this measure, we use it to assess goodness of fit of the logistic regression model. And it's based on the likelihood ratio test. I mean, this is kind of beyond this class, but it's good to know it. What does it mean and why we are using this one? So we can tell that the second model is much better compared to the first one. So we can say this here. So it's significant, yes. The squared h is still significant, yes, it is. Look at this one, the a or p is less than 0.05. Now the question says compute, not computer, compute the accuracy rate. So we will be using, or we are going to calculate the accuracy rate of the regression model. Let's go back to the initial model and use the first one. This is just to compare both of them. The second one is much better. It's better, but let's use the first one first. Find the accuracy rate for the first one and the accuracy rate for the second one, and see which one's more accurate in terms of predicting, or in terms of a predictive power, let's say. This is going to be kind of, first let's do the accuracy rate. Accuracy of the logistic regression model. I'm talking about the first one. This is going to be a little bit, we have first to discuss something. Where is it? We have to discuss something about the definition of the accuracy rate. What is the accuracy rate? The accuracy rate, if you remember, is the number of correct predictions divided by the total number of predictions. Again, what is the accuracy rate? The accuracy rate is the number of correct predictions divided by, or the ratio of, the total number of predictions. So we need first to calculate the probabilities. We have to find first the probabilities for each score. We have to find the probability for each score. So I'm going to do this carefully. I'm going to explain to you this carefully. After that, we are going to do this using the faster way. But I have to show you first what I'm going to do in the data. So now we have LTV, FICO, age. These are predictors, and we're trying to predict the default, right? So if a person comes to you with these scores, what is the predicted probability for him to default? So we're going to get another column. I'm going to add another column for you just to see. Contains the probability. Does that make sense? So my data, I'm going to add another column called estimated, estimated predicted, hold on, I'm going to call it p hat. It's the predicted defaulting, which is a predict, as you know. We're going to use logistic model, and we are going to, what is the data frame, what values you would like to create probability for, what values you would like to plug in into the model. All of my data. I'm going to plug in all of this observation. So this data frame, the whole data frame. Someone's going to tell me, what about the default? Oh, R is not going to look at this. It's going to look at these because you're specifying the type. The type is response. So when you do this, we are going to get the estimated probability of a person, of all of these people, to be defaulting. Let's go up here. So we got the p hat now. If a person comes to you with these scores, the probability that a person is going to default is is about 0. And it matches the observed value. It matches the real value, right? The goal is to classify, because remember, the goal of this problem is to predict and classify people. So how to classify? We are going to look at the probability. If the probability is greater than 0.5, then we're going to classify this person as a defaulter. So it's going to be 1. If the probability is less than 0.5, less than half, then the person is going to have a 0. He's not going to default. So we need to classify every case, every observation. To do this, I'm going to add another column, my data, called y hat. And how to do this? This is go back to chapter 2. We're gonna ask our R to look at this column. Look at this. If you see a number greater than or equal to half, give me 1. If you see a number less than 1, give me 0. So what I used F. So I'm going to use F else. Go to my data. Go to p hat. If you see a score first of all, look at the score. If it's greater than 0.5, return a value of 1, otherwise return 0. So we are adding a new column. This column, it's going to contain this. What is this? R is going to go to my data p hat, and he's going to see if it's greater than 0.5, he's going to put 1, otherwise he's going to put 0. Let me run this. What is that problem? If else. I like if else, the way that I did it. Else. L. Let's go up. Here we go. So the y hat, remember, the default is the y value, is the observed. This is the predicted, the estimated. So we are good. No, we are not good. We have now we have to see the number of correct predictions. We have to count them. Is the first one a correct prediction? Yes. The observed 0, the predicted 0. The second one, is it correct? Yes. 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 No. No. This is no. Number 9. So we have to count. We have to count if these values are equal. Look, if these values are equal, count them. So we're going to use a simple, very simple function, which is count these. Y hat, is it equal? No, let me use my data. My data, $, my Y hat. Is it equal? Is it equal to my data default? Are these equal? Yeah, but this is not enough. I'm going to put these between parentheses. And what I'm going to do, because this is going to give you what? My data, if they're equal, we're going to count them 1, 2, 3, etc. Then you would like to find the mean of this, the average. Because you're counting and dividing by the total number of predictions. This is the average, this is the mean. The mean, you're counting these true instances and divide by the total number of predictions. So we're going to find the mean of this. That's why we're using the mean. This is the accuracy rate. So this is the AR, accuracy rate. This is my accuracy rate. Run this, 91%. We have a really high accurate rate, but this is misleading. Remember, we will be talking about this because we don't know the nature of the data yet. Is it balanced or imbalanced? So don't look at, oh, we have high accuracy rate. We have to look at other measurements like sensitivity, for example, now. Because which case, what is our target class? Is it the 0? No. In the financial institution, the 0 is not their target class. The target class is the people who don't pay. Is the 1 is the target class. So they're going to look closely to the 1s, not the 0s, people. Right? So don't look at the accuracy rate and stop. No, we have to investigate, dig more. So we're going to talk about this after we finish this. But now we're going to do the accuracy. We're going to copy this and do it for the, for the other model, just for the sake of the model with quadratic term. So I'm going to copy all of this. Just I'm going to change a few things. I'm going to change this one to be quad logistic, right? So I'm going to add another 2 columns, p hat 0, p hat y hat 1. This is p hat 0. This is y hat 0. And we're going to compare to the default. So we're going to add another 2 columns, but this is using the second, remember, the second logistic model. I'm going to call this accuracy rate 0, accuracy rate 0. So make sure that we change everything. So I'm going to run all of these guys. So what we got 93%. It's higher accuracy rate, but it doesn't matter. Let me go back here. Look at the things that we have added. We have added 2 more guys. These are from the second model. These are from the first model, right? Do we need to add them as I did? No, there's no need actually, if you don't know. But this is just to show you. If you don't want to add them, just delete everything before the, the $sign. Let me delete this. Let me delete this. So let me delete this. But I cannot delete this because I'm comparing y hat with my data default. The default is from my data. It's here. It's embedded in my data originally. So I have to keep this. So watch it carefully. So do I need to delete this? Yes, be careful here. Yes. The same thing with these. Take this off. Take this off. Take this off. Take this off. This is enough. You can run this now. Everything's going to be perfect. 91, 93%. Would you like to remove what you have added here? You can run the file again. You can run the file again. You can go down there. Let me run. You can run the first code we started with. There are other methods, but this is enough. We can do this here. My data. Run this. Looking at my data, we got a clean one. There's no need to copy paste, by the way. Just you can run it from the top. The next recording, this has been 44 minutes. It's too long. We're going to continue, but we're going to do something very interesting. Hold out method. We're going to use hold out method. And we are going to this is perfect. Now we are testing our predictive power, and we see whether this the way that we have done it is where we have to do some adjustments. So let's continue this in the following video.